Hey everyone, welcome back to Probability Theory. This will be lecture 10 of the course. And in this section, we're going to sort of gently introduce random variables, the concept of a random variable. So let's go ahead and get started. And we'll refer to this section as section 1.10, 1.10, gentle introduction to random variables and numerical events. So here's the idea. When we're talking about, sort of the fields that leverage probability theory, we're talking about things like science, right? And of course, like engineering and business. Now, obviously, there are others, but these are broad categories. So even within science, you've got like everything from food science to physics. And inside of engineering, you've got your mechanical engineering, your electrical engineering, all of your variety. And then, of course, business is vast as well. So this covers a lot of space. Now, one of the things that you'll note as we kind of work through this, examples and as we kind of look further down into the course, what you'll see in general is that events of interest for these fields tend to be numeric. So science, engineering, business have a need for numeric events, right? And so the title of the section is numerical, has numerical events in it. That's all we're talking about are events that are assigned a number, right? So let's just talk through, just to make this concrete. What do we mean? Like, what are some examples? So an example for like the sciences would be like in medical science, the event that 100 of 100, we'll say, treated patients responds to the treatment. We've seen examples like this already. So you've got like you have you're testing a drug or something, and you have patients that have a certain condition, and you treat 100 of them. An event of interest would be that yes, 100 of them respond to the treatment, or 99 respond to the treatment, or 98. Right? The idea here is that your event of interest is numeric. Another example would be something like the event that a particular market will reach a certain price. So it's more like a business kind of example. The event that a market will reach 52,000 or 5,200. Right, so again, here you've got an event and you've got a numeric value corresponding to that event. And yet one more example, the event that stress loads will exceed a numeric threshold. This is like an engineering kind of example, right? So you've got an event and you've got some numeric value, like say it's 5,000 pounds or something. Okay, and so the whole idea here is just that in reality, in practical application, probability theory very often is interested in events that are numeric in nature. And so let's talk through how we can think about these in a concise way, in a convenient and efficient way. So if we let y denote variables like these, and so if we let y denote variables like these, i.e. numeric variables, and we grant, right, that the value of y will vary depending on the outcome of an experiment, And by experiment here, we mean a statistical experiment. So y is a numeric variable whose outcome varies depending on the results of some sort of statistical experiment. Well, really what we're defining here is a variable that is random, that has a random quality, right? So what we have described with y is called a random variable. Okay, right? So y is has a numeric value, and the value that you see when you look at y is, dependent upon the outcome of a statistical experiment, which is random, right? And so what we've described here is a variable that's random, i.e. a random variable. But let's talk about what a random variable is in a little more detail. Obviously, that's very loose and vague. But so the idea with a random variable is that if you start with a sample space, given a sample space, right? So I've got some space here, and I'm just going to break it up. You could kind of set it up however you want, but I'm just going to break it up into, we'll say, six events, right? So 6 events. So there's 6 items in my sample space. So given a sample space with 6 events, we'll say, okay, we can assign a number to each one of these events. So we could say this is number 1, this event is 1, this event has value 2, 3, 4, 5, 6. Now in practice, the assignment of the numbers to these events is meaningful, right? You don't just do it randomly. Generally, you say, well, this event corresponds to this number in this way. This other event corresponds to this number, to this different number in a different way, etc. Right? But here I'm just saying this event is labeled 1, 2, 3, 4, 5, 6. Right? So given a sample space, we can assign a number. We can assign a number to each of the events. Okay, right? Now notice what's happened here. Now each event is assigned to one and only one number. So each event is assigned to one and only one number, right? So that's the idea here. And so when you have a situation like this where you've got some number or something, in this case events, that corresponds to one and only one number, can you think of where I'm going with this? Can you think of what that's kind of a description of? It's kind of a description of a function, right? So if, because each event is assigned to one and only one number, we can think of y as a variable that is a function of the sample points in S. Y is a variable that is a function of the events in S. Okay. All right, so literally the domain of this function is the sample space, right? The domain of this function is the sample space. Okay, and so this brings us to the definition of a random variable. Okay, we say that a random variable is a real valued function for which the domain is a sample space. For which the domain is a sample space, right? So the value of the function, the value that the function is going to take, i.e. the value of y, has a random is randomly driven, right? So the value that goes into the function is, you know, the sample points in the sample space, and they're random, so therefore the variable will appear to be random as well. So that's the idea behind a random variable. Now we'll start with some examples here, but as I said, this is a gentle introduction, so don't worry. We'll see a lot more examples. I mean, throughout the rest of the entire course, we'll be continuously, discussing random variables. This is really fundamental. And so we just want a couple of examples to help us get a little bit comfortable with this idea. So here's an example. It's pretty straightforward. Consider an experiment where we toss 2 coins and observe the results. So we toss 2 coins and observe the results, right? And so we know what the sample space there looks like. You know, the first, you toss 2 coins, you could get maybe 2 heads. That's an event that can happen. Another one would be you get a heads on one, and then you get a tails on the other. Or maybe the reverse, you get a tails on the first and you get a heads on the second, whatever, right? Or they could both be tails, right? So this is really, this is the sample space. There are basically 4 outcomes to this experiment. You toss a coin, you get either 2 heads, 2 tails, or one of each. Okay, so we can define a random variable. So define y, the random variable, to be the number of heads in a toss. So the number of heads in a toss. Okay, and so what I want to do, so obviously this sample space is not numeric, but what I'm interested in doing is attaching a numeric value to the sample points in the sample space here. And how I define that random variable is I say y is the number of heads in a toss. Okay, and so if you think about that, you've got your HH, your HT, your TH, and your TT. So this guy here is the number of heads in a toss. That means the value of this is 2. These 2 here, the value is 1, and then this, of course, 2 tails, so the value is 0. And so y can take on the values of 0, 1, or 2. Those are the allowed, those are sort of the values that the random variable y can take on. Okay. Then, what we'll often want to know is the probability that y has a certain value, right? And so we denote that using this kind of notation. The probability that y, the random variable, is usually displayed kind of in this capital letter, as a capital letter, and equal to some other value, which we call little y here. Probability that y is equal to y is the sum. This is really calculated as the sum of the probabilities of the sample points that are assigned the value y. Little y, right? So this is very important right here. This is largely how we're going to be dealing with random variables, and so we're going to be interested in the probabilities. When we say the probability that y is equal to y, what we mean is just the sum of the probabilities of the sample points that are assigned the value of y. Right? So for example, the probability that y is equal to 0, well, we can look up here. We know how this works, right? 0 is assigned to this event, right? And that event is 1 of 4, so the probability that y is equal to 0 is 1/4. The probability that y is equal to 1, well, when we look back here, we can see that 1 is this one and this one. These two are both 1, so 1/4 and 1/4. So a half. And then the probability that y is equal to 2, of course, is just this guy. There was one event out of 4, that is corresponding to that value of 2, and so 1 in 4 again. Okay, so that's an example of how to think about probability, the probability of a numerical event, given that the sample space is not inherently numeric, right? You can kind of translate it into numeric using a random variable. Now, what about this example? Slightly more complex, but still pretty simple. Remember, we're just trying to get a kind of a gentle introduction here. Let's consider rolling a pair of dice, right? So you roll a pair of dice, 6-sided. Okay. And let X be the sum for a single dice roll. Okay, so I roll a pair of die and I get 2 numbers. I add them together, and that's the sum of the single dice roll, and X, the random variable, corresponds to that. So we can do the same kind of thing that we did before. Let's think about what sample space looks like, and so I'm going to draw it. So your first roll, you can get a 1, 2, 3, 4, 5, 6 on die 1. And then on die 2, you can get a 1, 2, 3, 4, 5, 6 also. Right? And then so the intersection, this is a convenient way to draw this, is just to think of the sample space as an intersection of all these numbers. And so of course you can have a 2. If you roll a 1 and another one, you get the sum, the value of X is 2. If you roll a 2 and a 1, the value of X is 3, and so on. Okay, and so you can see this looks like this, right? Okay. Okay, so the smallest value that X can take on is 2. The largest value that X can take on is 12. So X is equal to 2, 3, 4, and so on up to 12. Integer values, right? Of course. So if I were to say to you, what is the probability that X is equal to 5? Well, it's really easy. You can just kind of look in here, and you know there's 36 total values that X can take on. There's 36, so sorry, there's not 36 values X can take on. There's 10, but there's 36 items in the sample space. Each is equally likely, and the number of items in the sample space that correspond to the random variable 5 is 1, 2, 3, 4, right? So 4 out of 36. Okay, so the probability that X is equal to 5 is 4 in 36. What about the probability that X is greater than 10? So strictly greater than 10. Okay, well, there's 3 of those, right? So it can be 11 or 12. So this would be equal to the probability that X is equal to 11 plus the probability that X is equal to 12. Right, what's the probability that X is equal to 11? Well, it's 2 out of 36. And the probability that X is equal to 12 is 1 out of 36. Okay, so you've got that. All right, what about the probability that X is even? X is an even number, right? So, well, I mean, it could be the 2, it could be 4, any of these, 6, 8, 10, 12. So we want to say that it's 1/2. Is that right? Well, there's, let's see, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. So 18 over 36. So probability is 1/2. Okay. Very good. So that is a good place to stop. These are examples of kind of casting a familiar probability problem in terms of numerical events, i.e. sort of defining a random variable on a sample space And again, this is super useful. This is a lot of in actual application. This is how probability theory is generally used, at least in the sciences and the businesses. So we'll end it there. The next section, we will spend time reviewing, going over some example problems that we've covered thus far in the course. So we'll get into some more random variable examples in that section as well. So until then, take care.